in electrodynamics, we need to talk about two types. We're going to classify charges in two types. We're going to call them bound charges and free charges. Okay, so we talked about the hydrogen atom or a polarized hydrogen atom before, but let's just imagine that I have some insulating material right here. It's a block. And I put a charge right there. It doesn't really matter, there's an electric field, whatever. That electric field over here is going to induce dipoles over here. I'm going to draw some of those molecules. I'm going to do a terrible job. And they wouldn't all be lined up like this. But over here, we're going to get minus, plus, minus, plus, minus, plus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus. Okay, so the charge of that block is 0, right? But the charge density is not 0. So we're going to talk about this charge density here, where the total charge is 0. We're going to call that charge density rho b. We're going to call that bound charge. Because it's all there, right? That yes, they got split up and they cause a charge density, but the total charge is 0. That's the important thing, the total charge is 0. Now, imagine that I had something like this. So here's a plastic sphere, and I put a positive charge inside of there just for fun, and that's going to cause polarization like this, minus plus, minus plus, minus plus, minus plus, minus plus, one more, minus plus. Okay, you can see the idea. So that charge is not part of the material that would have a 0 total charge. So that's going to be rho f, free charge density. So we have these free and bound charge densities, and I just want to point out where they come from, right? The bound charge density is because the material gets polarized. And we've already talked about the dipole moment, but we need to talk about one more thing, and that's polarization. So one of the things I can do, each one of these has a dipole moment, right? But I can calculate the dipole moment per volume, and that's what we call the polarization. So I'm going to use the capital P. I don't like double decorations, right? That's a double decoration. It's got a vector and a line under it. I can't draw a capital. Can you draw a capital? I can't draw a capital. Okay, my capitals look the same. So this is going to be the dipole moment per unit volume. Now, a better way to write that is to say the dipole moment of material like that would just be the integral over the volume of the polarization integrated over the volume. Okay, so but that is a different thing. It's a different thing. It is related to the dipole moment, but it tells you because this, if I just say what the dipole moment is the whole thing, I have that, right? It acts like a dipole. But how does it change over the surface? That's what we want to know. Now, in this video, I want to show one thing, and I'm going to do it two ways in Python. One is that if I have some dipole moment or polarization of a material, then I actually get surface charges. Because right here, I get a negative and a positive, and they're right next to each other, so they don't really matter. But on the end over here, it's essentially as though I get some charge density over there, I get some charge density over there. So let's get an expression for the charge density as a function of the polarization vector. Now, this is a kind of a wonky derivation. The book has a much more robust derivation, but I like this because it just helps you see what's going on. So imagine I have some tiny little block. It's a cube, and it has a width of dx, and its volume is dx by dy by dz. And this has a polarization in the x direction. So I'm going to say the polarization is px x hat, and it doesn't have any y or z components. That polarization vector means that this is polarized, and I'm going to end up with positives on this side and minuses on that side. And that's going to be some charge q, and that's some charge minus q. Well, let's write the dipole moment for the whole thing. We can treat that, if it's super, super, super tiny, we can treat that as a negative charge and a positive charge separated by a distance dx. So the dipole moment P is going to be equal to q dx. x hat. Okay, so now, where did I go from here? I can't, okay, so this write the polarization in terms of the dipole moment. So the polarization, P, is going to be the dipole moment, P, I know, one's capital, one's lower e. Did you not hear that? Divided by the volume, but the volume of this is going to be dx, dy, dz. So it's the dipole moment per volume. And so it's a tiny little cube, so it has volume dx, dy, dz. Well, let's put in this. I get q dx x hat over dx, dy, dz. The dx's cancel. And so I get, that's fine. Now, if I'm on this surface, I have this n hat is a vector perpendicular to that surface. N hat would be equal to x hat. So if I take p dot n hat, that's going to be px x hat dot x hat, which is just 1, so just px. And so that's going to be equal to the x component of this, which is just q over dy dz. And look at this, dy dz is the area over here. So this is going to be q over dA, or sigma. I know that's kind of a not the best derivation, but then we do get this. The polarization vector dot n hat is equal to the surface charge density, where n hat is the unit vector perpendicular to the surface. Okay, because I could do the same thing in the y and the z direction. I'd get the same thing. And we can see that it doesn't really matter. What matters is this is the n hat for the surface. Not the best derivation. But now I'm going to do something better. I'm going to use this and take a sphere, and I am going to find the surface charge density on the surface of a sphere with a constant polarization vector. So here's my sphere, and let's say that I have a constant, these are the polarization vectors P in the z direction, and I want to use that to find the surface charge density. So here, the problem is that n hat is going to change directions, right? So I'm going to get positive charge on one side, negative charge on the other, and 0 in the middle. It shouldn't be too hard to calculate, but I want to visualize this in Python. Now, how do we deal with surfaces, spherical surfaces in Python, which is a Cartesian system? Python, WebVPython really likes Cartesian coordinates. Well, what I'm going to do is to do the following. And this is kind of a trick. So here's my sphere, and that's the z direction. And so I'm going to locate a piece right here. I have the angle theta, and that projects down to the angle phi in the x, I think this is phi actually, in the xy plane. And I have some little area right there on the surface. I'm going to draw it right there, dA. So what I want to do is to break theta into pieces and go that way. I'm going to break phi into pieces and go around that way. But the thing is that each one of those areas has a different size, right? Because I can't just say all these pieces are the same size, because spherical coordinates don't work that way. So if we think about this, first we can we need to convert this to Cartesian coordinates. So the vector r is going to be equal to the radius of this, which is capital R sine theta cosine phi x hat plus r sine theta sine phi y hat plus r cosine phi z hat. That's our conversion from spherical coordinates to Cartesian coordinates. And then I can calculate the length of this. So I can say, I'm going to say dl theta in the theta direction. It's just part of a circle. So this is going to be equal to dl is going to be equal to r times d theta, right? Because that's just part of the circle. Now, if I want to find dl in the phi direction, that's going to be r sine theta d phi, right? Because I have to project it down into the xy plane first. Did I get that right? Yeah. Okay. So what I'm going to do is to break this into 16 pieces, and I'm going to break the phi into 32 pieces because it's all the way around the circle. And then I'm gonna make my points, and then I'm gonna make little areas to represent each one, and they're gonna be little spheres, little cylinders. Now the nice thing about using little cylinders is that I can calculate n hat for each one of those pieces. Once I do that, then I can just take my p vector. I can do p dot n hat, which is going to be the axis of the cylinder, and then I can calculate the surface charge, and I'm going to display that as a color. And after that, what I'm going to do is come back to the board, but I'll put a charge over here instead of having, and then I'll have an induced dipole moment on the surface. I don't care about the inside, and I can use that to calculate the surface charge in C2. Okay, let's get started. I'm a little, I get a little anxious here because I know I can make a mistake and I don't want to make a mistake. So, but let's just get into it. So let's start off with the radius of our sphere, 0.1. I just picked something that doesn't really matter. I'm going to need this K as 1. That's my Coulomb constant. Q0, I'm going to need that later. That's going to be 1. Now I'm gonna need to vary theta and phi over the surface of this sphere. So let's start off with theta is 0, phi is 0, and now I'm gonna say d theta is gonna be equal to pi over 16. D phi is gonna be also pi over 16, which makes it 32 because it goes all the way around. You don't have to have these the same, right? They can be anything. But if you make them too small, it gets a little weird, but that's fine. Let's just put spheres here first, just so we can make sure that we're spreading things around the whole sphere. So what I'm going to do is say, what did I do this? I did phi. While phi is less than 2 times pi, goes all the way around, theta equals 0, while theta is less than pi. So once I go through my theta, I have to reset my theta back to 0 after I change my phi. So I'm just going to draw a sphere here. Let's just make a temporary vector. RT is going to be vector r times sine theta times cosine phi, r times sine theta. Can't even see that. Hello? Can't see. Okay. Sine theta times sine of phi, and then r times cosine of theta. That's my temporary location. Now I'm just going to put a sphere there. I'm not even going to add it to a list or anything. So just sphere position is going to be equal to RT. Radius is going to be, let's say, r over 30. I just picked that. Now I need to increase my value of theta, or phi. Phi equals phi plus d phi. And then I need to increase my value of theta. Theta equals theta plus d theta. And that should do it. Let's just see what kind of damage we did here. Uh-oh. Scared. Sometimes I have like a Wi-Fi problem and it doesn't. No, that looks good. I must have made a typo. Okay, theta is 0, phi is phi plus y. Oh, that's why. I wonder how many people saw that and were like, he did the wrong thing. And now sometimes when you catch this, it gets really mad and it won't run again. But let's just see. It takes some time. I think it maybe my network says, hey, you're blocked. I don't want to do. Let's just see if I can switch to this. Switch to my phone and run it, and then switch it back. Sometimes that works. Okay. Allow. Okay, run. So I'm running it on my cell phone now. No? This is one of the problems. Okay, let's do this. I think it's okay. Wow. Oh. I'm so dumb. Okay, I'm going to switch back to this. Real world. This is called real world stuff here. Okay. Real world mistakes. That's what we're making. What's the problem here? I'm going to have to start over, aren't I? Let's see. Okay, that's phi. Oh, this should be theta. This should be phi. And this should be... Oh, I got everything backwards. So phi theta equals theta plus d theta. No. Oh, they're both... That one should be theta. And this should be theta. What a mess. And you'd think, hey, why don't you start the video over? And that's what a normal person would do. But I'm already committed, and I don't want to do that. So phi equals phi plus... And what do you know? Maybe I did start it over, and this is my 5th time. Okay. Okay, got it. And it does look pretty, though, right? So that's pretty cool. Okay, so now what I want to do is to replace those with cylinders. Cylinders. So I'm also going to add these cylinders to a list so I can use them. So I'm going to say areas is an empty list. And then down here, instead of putting a sphere there, I'm going to put... the first thing I'm going to do is to calculate dl theta. That's going to be equal to r times d theta. dl phi is equal to r times sine theta times d phi, and then dA t, I'll call it, I'm not going to use that again. It's going to be equal to dl theta times dl phi, right? That's the area of my thing. I'm also going to need r, the radius, rad t. It's going to be equal to the square root, because that calculates the area as a piece, but I want it as a circle. So it's going to be dAt divided by pi. Pi r squared is the radius of a circle, or the area of a circle. So now I'm going to add areas equals areas plus cylinder POS equals RT. Axis is going to be equal to, let's say, R divided by 50 times norm RT. So what that does, and let me just put this up here. So the location of that piece is RT. Norm RT is a unit vector in that direction. So I'm setting the axis of that as a really thin thing, but in the direction of RT. So they're all oriented in the correct way. So that's the radius. No, now I need the radius. Radius is going to be equal to, they're all different radiuses. It's going to be rad t. And let's put, that's fine. I think that's it. So let's just run that. There we go. Nice. So there's my sphere, and I have all those areas. They're circles, right? They're not the way they should be, and they're not perfect, and these overlap way too much up here. That's why I have these gaps there, but it's fine. It'll work just fine for us. Okay, so now what I want to do is to define the polarization vector, P, and then calculate P dot n hat for each one of those spheres. So let's do that. So down here, let's just say P is... I'm going to say P0 is 1. I don't really know what it would be, but P is going to be P0 times vector 0, 0, 1. Okay, P0, that's the polarization. It's constant. It's throughout the whole thing. Now I can go through all of my areas and calculate P dot n hat. I can do that, not too bad. So for area in areas, so for each area, I know P. I'm just going to take P and dot n hat. That's pretty easy. So I'm going to call that sig. Sig is equal to the dot product of P, and n hat is going to be area. It's going to, I'll put this as norm area dot axis. That's the charge density for that. Okay, now I want to calculate the charge for each thing. So the charge for each thing, all those circles have different areas, right? And so I could just use the charge density, but let's just calculate the charge on each one. So the charge on each one, I'll call it dq, is going to be sig times area dot dA. Did I put dA in my areas? I did not, but I'm going to put that right over here. So I'm going to put dA equals dAt. Right, so I calculated that area, so it's a property associated with that little circle, so that's kind of cool. Now what I want to do is to put the color of the charge. So positive is red, negative is blue. So if dq is greater than 0, then area.color equals color.red. If dq less than 0, area.color equals color.blue. Now you may say, well, you could just say if else, but this means that if it is 0, then it stays white. Okay. Let's see what happens. Okay, so this is exactly what we'd expect to happen, right? Half is red, half is blue. But it doesn't display the density of the charge. So what I want to do is to change the opacity of the system so that the higher density charge, higher charge is going to be more opaque, less dense is less opaque. So let's just say area.opacity equals dq. Because if dq is 0, it'd be clear and you wouldn't see anything. And then down here, I'm going to say area.opacity equals negative dq, because opacity is a number between 0 and 1. And so if the charge is negative, it would be below 0 and needs to be clear. Okay, now, if I want the maximum charge to be 1, so let's just see what happens. I can just adjust that manually. Now, see, they're all too small. So let's just take, let's say dq times 10. Times 10. I'm just guessing here. I could print out dq, but nope. Let's just do this. I'm going to print, let's just print it. Print dq. That's going to be a whole bunch, but who cares? 10 to the negative fifth. Okay, so we're talking about, let's see, what's my maximum here? 7.35 times 10 to the negative fifth. I want that to be 1. No, I want my maximum. I want this one to be, this one right here. That to be 1. So let's just say, let's call that a constant. I'm going to call it con equals that. So now I'm going to take the opacity as this divided by the constant. That should do it. And then the maximum would be 1. There we go. Okay. And so you see over here, it's not, you see right there, there's no charge and you can see through it. It's a little bit, I want a little bit, I think that's fine. Yeah. I think because the size of the things, that's what we get. Okay, now what I want to do is to put a charge outside there and redo the experiment. So the only thing I need to do is to calculate the dipole moment for each one of these, and then use that to calculate the polarization. So I do not have constant polarization. Let's just do this. It shouldn't be too hard. The first thing I'm going to do is up here, I'm going to add a charge. Q1 is a sphere. Position is going to be equal to vector. I did that already. Let's say 1.5 times r, 0, 2 times r. I'm just picking some values. And then the radius is going to be equal to r divided by 20. Color equals color.red. It's a positive charge. Let's just run that and see what it looks like. Where'd it go? There it is. It's just a bad location. It's right there. That's fine. Now I'm going to define a function that calculates the electric field. Def E-R-O-T. So I only have 1 point charge I need to calculate the electric field for. So I'm going to say RT is the observation location minus Q1.POS, right? Because I'm talking about the electric field due to that positive charge. And then I can just return K times Q0 times norm RT divided by mag RT squared. Now I need to calculate, I already have my areas. Instead of P as some constant value up here, I'm going to calculate P. So I'm going to calculate P right here while I go through my areas. So P is going to be, no, this is lowercase p. Oh no, yeah, so one of the things we're going to use is P is alpha times the electric field. So I'm going to put an alpha here. Alpha is 0.01, just picking a value, right? So that says as linearly polarization. So the polarization is in the direction of the electric field. So is this P or P? Is it capital P or lowercase p? I think it would be P, but so let's just do this. P is going to be equal to alpha times E of area.POS. That's the location I want it. But then I have to divide by the volume. So the volume is actually going to be the area, right, times some thickness. So let's just say divided by area.dA. So now I have the polarization vector. And then everything else is the same down here, right? So I'm still going to find the sigma and all that stuff. I'm going to have to change my my value for. Okay, so this is actually pretty good. I didn't change the charge density. I'm not gonna fuddle around with that. But look, so there's my charge up there. It's going to have negative charge on this side of the sphere, positive charge on that side. It's not uniform, right? Because this stuff is closer, so you're going to have a non-uniform polarization vector. So this is kind of cool. I kind of like it. I'm kind of happy. I would like to change the opacity of it, but I don't want to mess around with the constants. That can be your homework for you. So that's polarization in electrodynamics. The end. I'll talk to you later.